China establishes world's first three-satellite constellation in the Earth-Moon region. On April 16, 2025, China announced a groundbreaking achievement in space exploration by establishing the world's first three-satellite constellation in the Distant Retrograde Orbit (DRO) within the Earth-Moon region. This development is a significant leap towards the exploration and utilization of cislunar space, which extends up to 2 million kilometers from Earth. Background and development timeline. The journey towards this monumental achievement began in 2017 when the Chinese Academy of Sciences (CAS) initiated preliminary research and technological development focused on the Earth-Moon region, particularly the DRO. In February 2022, CAS launched a pilot project aimed at creating a large-scale satellite constellation in the DRO. This project culminated in a series of satellite launches. 1. DRO-L, launched on February 3, 2024 into a sun-synchronous orbit. This satellite began its experimental phase as planned. 2. DRO-A and DRO-B. These two satellites were launched on March 13, 2024 but encountered a setback when they failed to reach their intended orbit due to a rocket anomaly. However, following a series of emergency maneuvers, they successfully achieved their designated positions in the DRO on July 15, 2024. 3. Constellation formation. The three satellites successfully established inter-satellite communication and measurement links by August 2024, marking the completion of the first constellation in the DRO. Understanding Distant Retrograde Orbit (DRO). The Distant Retrograde Orbit is a unique type of orbit characterized by its stability and low fuel requirements for spacecraft. This makes it an ideal hub for connecting Earth, the Moon, and deep space, thus enhancing the operational capabilities for future lunar missions and interplanetary exploration. Technological innovations and breakthroughs. The establishment of the three-satellite constellation has led to several technological breakthroughs. Low-energy insertion. The constellation achieved a historic milestone by successfully completing the world's first low-energy insertion into a DRO using only 1/5 of the fuel typically required for such maneuvers. This significant reduction in fuel consumption could drastically lower the costs associated with accessing cislunar space. Inter-satellite communication. The team validated a K-band microwave inter-satellite communication link over 1.17 million kilometers of feet that overcame significant technological barriers previously faced in establishing large-scale constellations in cislunar space. Orbit Determination System. A new satellite-to-satellite orbit determination system was developed, enhancing tracking accuracy by utilizing inter-satellite data rather than traditional ground-based methods. This innovation allowed for orbit determination precision equivalent to over 2 days of traditional ground tracking using only 3 hours of inter-satellite measurement data. Scientific applications and future prospects. The constellation supports various scientific research initiatives including astrophysical studies, quantum mechanics, and atomic physics. The stability of the DRO provides an effective platform for these explorations, allowing scientists to conduct fundamental research in these fields. In addition to scientific research, the constellation is expected to play a crucial role in future lunar exploration missions by providing rapid orbit determination and autonomous navigation services for lunar orbiters. The long-range communication capabilities established through the constellation will also facilitate the downlink of critical data during lunar missions. Strategic importance. This achievement is strategically significant for China as it seeks to exploit lunar resources, support long-term human habitation beyond Earth, and engage in interplanetary activities. The operational capabilities provided by this constellation are anticipated to enhance navigation and data transmission for upcoming lunar missions, thus making them more efficient and cost-effective. China's advancements in space are not just limited to technological innovation, they also reflect a broader ambition to establish a strong presence in the emerging commercial activities in cislunar space. The success of the three-satellite constellation is a testament to China's commitment to leading in space exploration and technology. Conclusion. China's establishment of the three-satellite constellation in the Earth-Moon region marks a significant milestone in the landscape of space exploration. It not only showcases the country's technological prowess but also sets the stage for new scientific discoveries and potential commercial ventures in cislunar space. As the world watches these developments unfold, China's role in the future of space exploration is poised to expand further, opening up new frontiers for humanity. Counterintuitive information from the content includes 1. Low energy consumption. The ability to enter the distant retrograde orbit DRO using only 1/5 of the fuel typically required for such maneuvers contrasts with conventional wisdom that deeper space missions necessitate significant energy expenditure. This innovative approach challenges traditional assumptions about fuel requirements for space exploration. 2. Satellite recovery. The successful recovery of the DRO-A and DRO-B satellites after a failed initial launch due to a rocket anomaly is a remarkable feat that goes against the expectation that such failures would typically result in mission loss. The ability to execute emergency maneuvers to correct their trajectory demonstrates a level of flexibility and adaptability not commonly associated with satellite missions. 3. Inter-satellite communication. The establishment of a K-band microwave inter-satellite communication link over 1.17 million kilometers contradicts the expectation that long-distance communication in space would be significantly challenging. This breakthrough indicates that advanced communication systems can overcome technological barriers more effectively than previously thought. 4. Orbit Determination System. The new space-based orbit determination system, which uses inter-satellite data to achieve precision that would normally require 2 days of ground-based tracking in just 3 hours, challenges the assumption that ground-based tracking is essential for accurate navigation in space. This innovation suggests that satellite-to-satellite tracking can be equally or more effective, potentially transforming operational methodologies in space exploration. 5. Strategic resource exploitation. The strategic importance of the DRO for lunar resource utilization and commercial activities in cislunar space challenges the narrative that deep space exploration is solely for scientific discovery. This highlights a shift towards considering the economic potential of space exploration, which is often overlooked in favor of purely scientific objectives. These points illustrate that advancements in technology and innovative problem-solving can lead to outcomes that defy conventional expectations in space exploration. China's establishment of the world's first three-satellite constellation in the distant retrograde orbit DRO within the Earth-Moon region is a landmark achievement that carries significant implications for the future of space exploration, scientific research, and potential commercial activities. While the general narrative surrounding this development has been widely reported, certain critical aspects are often overlooked which are essential for understanding the broader significance of this achievement. 1. The technological breakthroughs. A key point that may be undervalued is the technological advancements achieved during this project, particularly regarding the low-energy insertion into the DRO. This accomplishment, which utilized only 1/5 of the fuel typically required, represents a paradigm shift in how spacecraft can access cislunar space. The implications of this breakthrough extend beyond mere cost savings. It fundamentally alters the feasibility of more frequent and larger-scale missions to the Moon and beyond. Reduced fuel requirements mean that spacecraft can carry more payload, thereby enhancing mission capabilities and potentially leading to more ambitious exploration objectives. 2. Inter-satellite communication innovations. The establishment of a K-band microwave inter-satellite communication link over 1.17 million kilometers is another technological feat that deserves greater attention. This achievement not only facilitates effective communication within the constellation but also sets a precedent for future satellite networks. The ability to maintain such long-distance communication significantly enhances the operational efficiency of space missions, allowing for real-time data exchange and improved coordination between satellites. This capability is crucial for the success of future lunar missions, where timely decision-making can be the difference between mission success and failure. 3. autonomous navigation and orbital tracking. The development of a satellite-to-satellite orbit determination system marks another area of innovation that is often glossed over. This system enables satellites to track each other without relying on ground-based stations, significantly increasing the operational autonomy of space missions. By achieving orbit determination accuracy equivalent to 2 days of traditional ground tracking in just 3 hours of inter-satellite measurements, this advancement reduces the cost and complexity of tracking and controlling spacecraft in cislunar space. This capability is especially important for missions operating far from Earth, where ground-based support may be limited or delayed. 4. Influence on scientific research. The constellation's potential to support scientific research initiatives in fields such as astrophysics, quantum mechanics, and atomic physics is another critical aspect that could be overlooked. The DRO stability allows for long-term experiments that can yield valuable data, contributing to our understanding of fundamental scientific principles. The ability to conduct such research in a unique orbital environment can lead to new discoveries that may not be possible in other settings. This positioning of China at the forefront of cislunar scientific research could enhance its global standing in the scientific community and foster international collaborations. 5. Strategic implications for cislunar space. The strategic importance of cislunar space extends beyond scientific research and into geopolitical considerations. The ability to establish a presence in the Earth-Moon region positions China favorably in the emerging space economy, particularly as nations and private entities increasingly recognize the potential for lunar resource exploitation. The establishment of this satellite constellation is not merely about technological prowess, it is also a strategic move in the broader context of space governance and resource management. As other nations, including the United States, ramp up their own lunar ambitions, China's advancements in this area could influence international policies and agreements regarding space exploration and resource utilization. 6. Long-term human habitation and lunar commercialization. The constellation's role in supporting long-term human habitation beyond Earth is another significant but often understated aspect. The technologies and infrastructure developed through this project could be critical for establishing sustainable human presence on the Moon. The potential for commercial activities in cislunar space, including mining and tourism, hinges on the successful deployment and operation of such satellite networks. By laying the groundwork for future lunar colonies and commercial ventures, China is positioning itself as a leader in the next era of space exploration. 7. International collaboration and competition. While the narrative around technological achievement is prominent, the implications for international collaboration and competition in space exploration deserve mention. The establishment of this constellation reflects China's commitment to advancing its capabilities in space, potentially leading to heightened competition with other spacefaring nations. However, it also opens avenues for collaboration, particularly in scientific research and exploration initiatives. As cislunar space becomes a focal point for various nations, the potential for collaborative efforts on shared goals such as lunar research and sustainability could emerge alongside competitive dynamics. Conclusion. China's establishment of a 3-satellite constellation in the Earth-Moon region is a multifaceted achievement that transcends the initial reporting of successful satellite launches and operational capabilities. The technological breakthroughs, strategic implications, and potential for scientific advancement are significant aspects that warrant greater recognition. This development not only positions China at the forefront of space exploration but also sets the stage for a new era of international collaboration and competition in cislunar space, which will shape the future of humanity's endeavors beyond Earth. Understanding these nuances is crucial for comprehending the full impact of China's achievements in space exploration. 1. Technological innovations and breakthroughs. China's establishment of the world's first 3-satellite constellation in the Distant Retrograde Orbit (DRO) represents a significant leap in space technology. Key innovations include the world's first successful low-energy insertion into a DRO using only 1/5 of the fuel typically required for such maneuvers. Additionally, the development of a K-band microwave inter-satellite communication link verified over 1.17 million kilometers overcomes substantial barriers in creating large-scale constellations in cislunar space. These advancements not only enhance the efficiency of satellite operations but also pave the way for future deep space exploration missions. 2. Strategic importance of cislunar space. The establishment of the satellite constellation is crucial for China's ambitions in cislunar space, which is viewed as a strategic domain for resource exploitation, long-term human habitation beyond Earth, and interplanetary activities. The DRO's stability allows for efficient navigation and data transmission, which are essential for future lunar missions and potential commercial activities in this region. This strategic positioning could enhance China's role in global space exploration and resource utilization, potentially leading to increased geopolitical influence. 3. Scientific applications and research opportunities. The constellation supports a range of scientific research initiatives including astrophysics, quantum mechanics, and atomic physics. The DRO's unique environment allows for long-term stability, making it an ideal platform for fundamental scientific research. This capability not only enhances our understanding of the universe but also contributes to the development of new technologies and methodologies in space science, thereby solidifying China's position as a leader in space exploration and research. 4. Challenges and future directions. The launch of the DRO-A and DRO-B satellites faced significant challenges, including initial failure to reach their intended orbits due to a rocket anomaly. The successful recovery and establishment of inter-satellite links demonstrate China's resilience and adaptability in complex mission scenarios. Moving forward, the research team aims to explore the diverse orbits in the Earth-Moon space and conduct further studies on the lunar environment. This ongoing research is expected to yield new insights and capabilities that will drive future lunar exploration and the establishment of a sustainable human presence beyond Earth. Here are 3 famous historical cases that reflect significant achievements in space exploration akin to China's establishment of a 3-satellite constellation in the Earth-Moon region. 1. Apollo Program 1961–1972. The Apollo program, conducted by NASA, was a monumental series of missions aimed at landing humans on the Moon and safely returning them to Earth. The most notable mission, Apollo 11, achieved this historic feat on July 20, 1969, when astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface. The program not only succeeded in its primary goal of lunar exploration but also advanced various technologies in rocketry, computer science, and telecommunications. The success of Apollo laid the groundwork for future space exploration and showcased the potential for human habitation beyond Earth. 2. International Space Station 1998–present. The International Space Station (ISS) represents a collaborative effort among multiple nations including the United States, Russia, Europe, Japan, and Canada to create a habitable space environment for scientific research and international cooperation in space exploration. Launched in 1998, the ISS serves as a microgravity laboratory and a platform for experiments in various fields including biology, physics, and astronomy. The ISS has demonstrated the feasibility of long-term human presence in space, contributing to our understanding of life sciences in microgravity and paving the way for future missions to the Moon and Mars. 3. Mars rover missions 2004–present. NASA's Mars rover missions, particularly the Spirit and Opportunity rovers 2004 and more recently the Perseverance rover 2021, have significantly enhanced our understanding of the Martian environment and the potential for past life on the planet. Spirit and Opportunity conducted extensive geological surveys, while Perseverance is equipped with advanced scientific instruments designed to search for signs of ancient microbial life and collect samples for future return to Earth. These missions exemplify the technological advancements in robotics and autonomous navigation, mirroring the technological innovations achieved by China's satellite constellation in the Earth-Moon region. The ongoing exploration of Mars continues to inspire global interest in space science and the quest for extraterrestrial life. Future outlook: predictions for China's three-satellite constellation in the Earth-Moon region. The establishment of China's first three-satellite constellation in the Distant Retrograde Orbit DRO represents a significant milestone in space exploration with implications for both scientific research and commercial activities in cislunar space. Here are some predictions regarding the future impact and developments stemming from this groundbreaking achievement. 1. Enhanced lunar exploration missions. China's three-satellite constellation is expected to play a crucial role in upcoming lunar exploration missions. With its ability to provide real-time data and navigation support, the constellation will enhance the efficiency and safety of crewed and uncrewed lunar landers. Future missions may include more ambitious objectives such as lunar base construction and resource extraction, positioning China as a leader in lunar exploration. 2. Technological advances in satellite communication. The successful validation of K-band microwave communication links between the satellites showcases a significant technological breakthrough. Over the next decade, we can anticipate further advancements in satellite communication technologies, which may lead to the development of more extensive cislunar communication networks. Such networks could facilitate faster data transmission between Earth and lunar missions, ultimately supporting more complex operations and experiments. 3. Commercial opportunities in cislunar space. As the DRO offers a stable platform for operations, the potential for commercial activities in cislunar space is vast. We can expect increased interest from private companies and international partners in leveraging the capabilities of this constellation for resource mining, satellite servicing, and other commercial ventures. This could lead to a new economic ecosystem focused on the utilization of lunar resources such as water ice for fuel and construction materials. 4. International collaboration and competition. China's advancements in cislunar exploration may prompt a new era of international collaboration and competition in space. Other nations and private entities may seek partnerships with China to access its satellite constellation's capabilities while simultaneously working on their own lunar ambitions. This dynamic could foster a collaborative environment for scientific research and exploration, or conversely lead to geopolitical tensions as countries vie for dominance in cislunar space. 5. Innovations in astrophysical research. The constellation's stability allows for long-term scientific observations and experiments. We predict that it will facilitate significant breakthroughs in astrophysical research, particularly in fields such as quantum mechanics and atomic physics. This could lead to novel discoveries that enhance our understanding of the universe and contribute to technological advancements on Earth. 6. Development of autonomous navigation systems. As researchers continue to refine satellite-to-satellite tracking and autonomous navigation systems, we can expect these technologies to become more prevalent. Future spacecraft will likely employ these systems for precise navigation and orbit determination, leading to safer and more efficient missions. This technology may eventually be adapted for use in commercial aircraft and autonomous vehicles on Earth. 7. Long-term human habitation beyond Earth. China's ambitions for long-term habitation on the Moon will likely be bolstered by the capabilities provided by the three-satellite constellation. As infrastructure is developed for lunar habitation, the constellation will support the necessary communication and navigation systems required for sustaining human life on the Moon. This could pave the way for the first permanent lunar base, serving as a hub for further deep space exploration. 8. Environmental monitoring and Earth science applications. The constellation's capabilities may extend beyond lunar missions to include Earth observation and environmental monitoring. Data collected from the satellites could be used to enhance our understanding of climate change, natural disasters, and other global issues. This dual functionality would maximize the investment in the constellation and contribute to the broader scientific community. 9. Educational and research opportunities. The advancements stemming from this project may inspire a new generation of scientists and engineers. Educational institutions may develop specialized programs focusing on space technology, astrodynamics, and satellite communications, fostering international collaboration and innovation in these fields. This shift could lead to increased participation in STEM science, technology, engineering, and mathematics disciplines globally. 10. A blueprint for future deep space missions. Finally, the technologies and strategies developed through the 3-satellite constellation will likely serve as a blueprint for future deep space missions beyond the Moon. As humanity aims for Mars and beyond, the lessons learned from operating in the Earth-Moon region will be invaluable, guiding the design and execution of interplanetary missions. Conclusion. China's establishment of the world's first 3-satellite constellation in the Earth-Moon region is a transformative step in space exploration. The future of this initiative holds immense potential for lunar exploration, commercial activities, scientific research, and international collaboration. As these developments unfold, we will witness a new era of space exploration that will shape humanity's journey beyond Earth for generations to come.